Which particles are found in the nucleus of an argon atom? We should know that in the nucleus there lies protons and neutrons. The diagram below shows a particle traveling through an electric field. And we have a positively charged plate and a negatively charged plate. Now, which particle remains undeflected when passing through the electric field? So, think about this, right? If you have some sort of particle, right? Let's say if the particle is positively charged. Well, we have to know is that opposites attract. So basically, the positively charged thing is going to get attracted to the negatively charged thing. So it's going to get deflected. If you have a negatively charged thing, it's going to get attracted to the positively charged thing, right? Opposites attract. Now, the thing is that if a particle has actually no charge at all, so let's say if the particle has no charge, well, then it's not going to be attracted to either of these. It's just going to go straight through. So the answer is going to be number 3, neutron. The mass of electron, well, you should know that electrons are they weigh way less than a proton or a neutron. Okay, so it's going to be less than the mass of a neutron. All right. Compared to the energy of an electron in the second shell of the atom of sulfur, the energy in an electron in the. Okay, so what you got to know is you have to know something called the Bohr's model of the atom. So basically, let's say if this is a model of the atom, where in the center I've drawn the nucleus, and then right over here, all of these rings represent basically electron shells, basically regions where an electron, could go to. All right. So these are basically, let's just say, these are kind of the locations where the electron can sort of like orbit around the atom. This is why this model of the atom is also called a planetary model. Now, an atom can move into a higher shell if it gains energy. So if this atom right over here, or this electron gains energy, it can actually move up in energy level. So the electron in the highest energy level will have the most energy because, well, it takes more energy to go from I'm just gonna put it like this, right? Going from the first shell, right, basically the first ring to the second ring, that's gonna take some energy. But going from the first ring to the third ring, that's gonna take more energy, right? Because you have to move up more shells. All right. And actually, when an atom goes from a higher energy level back down to a lower energy level, it's actually gonna release that energy that it gained as light. All right. So yeah, compared to energy of blah blah blah. Well, the answer right over here, and second shell, it should be first shell is lower, right? If an electron is in the second shell of the atom, it's going to have more energy than an electron in the first shell of the atom, right? Because it has absorbed some energy, right? All right, in the ground state, an atom of which element has 7 valence electrons? So how do we solve this? And for this, you could just use your periodic table. So let me pull it up. Now, each group right over here, there's something known as groups in the periodic table. So basically, a group is I forgot if this is a row or a column. I think this is a column. I think this is called a column. All right, it's an up and down thing. All right, basically things in the same up and down area. There's something known as a group. All right. Now, group one is this. Okay. This is group two. This is group one, which is the alkaline metals. Alkaline metals are very reactive. You might have seen a video of alkaline metals react with water, very violent, and it gets more violent as you go down the group. This is group two, alkaline earth metals, and then we're going to skip the transition metals. The transition metals are a little bit funky, so we're going to skip those. This right over here it's group 13, but think of it as group 3A. Okay. This is group 14, also known as group 4A, pretty much. Group 15 is group 5A. Group 16 is group 6A. 17, 7A. 18, 8A. Now, the thing is that the things inside the same group, they're going to have the same amount of valence electrons. So in this case, group 1 right over here, right, we have an atom of lithium, we have an atom of sodium. They're all in the same group. And it turns out that both of them have 1 valence electron. Both of them have 1 valence electron. If you look at group, let's say if you look at group 7A, if we take a look at an atom of fluorine or an atom of chlorine, they both have 7 valence electrons. So notice how the amount of valence electrons that they have pretty much just match up with their group number. All right. So what The key concept I want y'all to understand is that atoms in the same group, they got the same amount of valence electrons. And valence electrons just means the electron that's in the outermost shell of the atom, right? If I draw the planetary model again, it's the electron that's like that furthest away from the nucleus, right? It's the outermost shell. Now we want to find out atom with 7 valence electrons. So which atom is in group 7A? So group 7A, that's going to be fluorine, right? Fluorine is in group 7A, so that's going to be the answer, right? So I'll just, your periodic table, just kind of carrying this. Oh, I also have stuff from the roots video, so, watch that. All right, so that's going to be fluorine. Which information is sufficient to differentiate a sample of sodium from a sample of silver? Mass of each sample, reactivity, the phase of each sample at room temperature. It has to be 3, man. Because, in order to determine one thing from another, A and B, well, it's not enough to, just measure the mass or measure the volume of each sample. Because think about it. What if they weigh the same, right? If I gave you some sodium, which is a sort of gray metal, right? It's a metal. And if I gave you silver, which is also a gray metal, let's say if they weigh the same, they have the same mass. I know weight and mass are not the same thing, but let's just keep that out for now. Let's just say, all right, their mass is the same, okay? Now, how would you tell the difference? If the mass of both of these were the same, how the hell are you going to tell the difference? If they have the same volume, how are you going to tell the difference, right? That's not enough. What you really need to know is how they react, okay? The reactivity of each sample with water. Because a lot of times, what actually helps you differentiate one thing from another thing is actually chemical properties. How they react, basically, right? Their kind of atomic structure, right? Chemical properties help you determine to, kind of separate one thing from the other thing. If you were just take a look at it, or you just to kind of feel it, that's something known as basically physical properties, right? It's how they basically look, physical properties, or it's how they look, or it's how they feel, right? That's the physical property. But when you want to differentiate one thing from the other, you got to focus on the chemical properties, how they react. And I'm sure that I don't know, but you might have saw a video of alkaline. I already said this before, but you might have seen a video where somebody puts alkaline metals in kind of a container filled with water, and it's very reactive. So if you have not seen that, I highly check it out. But it turns out that alkaline metals are very reactive with water. So it makes sense that, if you want to differentiate sodium from silver, place it in water, and you'll find out the sodium reacts a lot. All right. Graphite and diamond are 2 forms of solid carbon at STP. These forms have, so we have to know as these 2 things are something known as allotropes of each other. Allotropes have different molecular structures, and therefore they have different sort of properties, okay? Let me show you. Now, I'm not actually going to draw out the carbon structures, I'm sorry. You got to Google them up because I'm a little too lazy. But basically, diamonds, they have like a very rigid, pretty sure tetrahedral structure, and that's what makes diamonds very hard. While graphite, it's more of like a layered structure, all right, which kind of explains why graphite's a little bit sort of less hard, obviously, right? If you're looking at graphite versus diamond's hella hard. In addition, graphite also conducts electricity. The carbon atom, pretty sure it has 1 delocalized electron in it. So the electron basically moves freely around the atom. And when a charge, like an electron, so when something has a charge and it's moving, right? Then it's going to be pretty good at conducting electricity. So yeah, pretty much just free moving charges, like electrons, like charged particles, right? When they move, that's going to allow the graphite to conduct electricity. All right, first 5 elements on group 14, top to bottom, there are changes in what? First shell, number of valence shell electrons, atomic radii, and electronegativity values at top. So when you're looking at a group, remember that in a group you have the same amount of valence electrons. So we can immediately eliminate number 1, and also number 2. In group 14 is all of these atoms right over here. And the thing is that, look, you also have these little numbers at the bottom. And what they tell you is basically the electron configuration for that atom. So basically, with this 2,5 right over here is saying for nitrogen, is that nitrogen has 2 electrons in the first shell and 5 electrons in the second shell. That's basically what it's saying, right? And notice how for group 14, all of them start with a 2, meaning that all of them have a 2 and 2 electrons in the first shell. So we can immediately eliminate number 2. Yeah, this one has valence shell electrons, right? But we know that that's the same in atoms of the same group, so it has to be electronegativity. Now, it's also good to explain why. Why does electronegativity change throughout a group, and why does atomic radii change throughout the group? So, electronegativity, I'm just going to say En, and we also have atomic radii. Atomic radii. Electronegativity is basically how well does an atom sort of attract an electron. All right. Now, actually, let's talk about atomic radius first, because then electronegativity makes sense. All right. So atomic radius, it's basically, if you have an atom right over here, it's the distance between the nucleus of the atom and the outermost shell. It's basically, I mean, it's kind of what it sounds like, right? It's the radius of the atom, essentially how big the atom is. And as you go down a group, the atoms get bigger. And it kind of makes sense because, I mean, notice how as you're going down a group, you're adding more shells. So in an atom of fluorine, you have 2 shells, right? You have 2 electrons in the first shell, 7 in the second shell. For chlorine, you're adding another shell. In this case, there's 3 shells now. There's 4 shells in bromine. There's 5 shells in iodine, right? So you can imagine that it kind of makes logical sense. If you have an atom of fluorine, which has 2 shells, then you have an atom of chlorine, which has 3 shells, right? It's going to be bigger, right? Because it just has more shells, right? So that makes sense. So as you go down a group, atomic radius increases. Now, electronegativity, well, that basically just explains how well does an atom attract electrons. And it turns out that as you go up a group, the electronegativity is going to increase. Because when you go up a group, remember, atoms get smaller, right? We said how as we go down a group, our atoms get bigger. So if we go up a group, our atoms get smaller. And if the atom gets smaller, then if an electron comes, well, it's more likely to get attracted to it. Meanwhile, if the atom's a little too big, well, the electron is less likely to get attracted because the nucleus is just so far away. And if you're looking at something known as Coulomb's law, you'll actually find out that the further away the two things are, it's going to have a very big impact on sort of the attraction between the two things. It's sort of like magnets, right? You have 2 magnets right over here. They might have a strong charge for each other if you place them very close to each other, right? If you place 2 magnets very close to each other, it's going to have a very strong attraction. But if you increase the distance, it's going to have a much weaker attraction. All right. So which statement describes why this is a compound? All right, yeah, this is just going to be 1. I mean, literally the definition of a compound, I mean, these 2 things are chemically combined and they're in a fixed proportion, right? If you were to take a look at something like H2O, H2O is water. It contains 2 part hydrogen, 1 part oxygen. If I have something like, let's say, H3O plus, notice how, I mean, if we're ignoring the charge, notice how it's in a different ratio, right? There's 3 parts hydrogen to 1 part oxygen. Therefore, this is not water, all right? If in order for something to be water, you need exactly 2 parts hydrogen, 1 part oxygen, pure water, all right? So yeah, they are chemically combined, right? Not just physically mixed. Like if I mixed like water and like let's say salt together, that's not a compound. That's something known as a mixture because you're just like physically mixing them together. But for compounds, it's chemically combined by chemical bonds, and it's in a fixed proportion, meaning that it's a fixed proportion, right? It's 2 parts hydrogen, 1 part oxygen. All right. 2 types of chemical formulas. All right, so the 2 types of formulas, endothermic and exothermic, basically describe whether a reaction releases or absorbs heat. That is not a chemical formula. This is also fusion and fission are types of chemical reactions, some nuclear reactions, right? But they are not chemical formulas. Oxidation, reduction. Oxidation, you lose electrons. Reduction, you gain electrons. That is also not it. Empirical and structural are the way. Structural, it's in the name, right? It's the structure. It's the actual structure of the atom. Empirical, you can think about it as the simplified version of a molecular formula. So, I mean, it's basically like, all right, so here's what I'm talking about. let's say if we have glucose, C6H12O6. All right. Now, this is the molecular formula for it, right? It shows all the atoms, right? It shows all the atoms in glucose. Now, the empirical formula, it's sort of like the simplified version of the molecular formula. The empirical formula for glucose is just going to be CH2O, right? Because notice how all of these have a common factor of 6. So it's like, imagine if you divided this by 6. I know this is kind of cursed, but imagine if you divided this by 6. You're going to get this right over here. All right, that's sort of like the empirical formula, right? It's sort of like the simplified version of the molecular formula. All right, charge, mass, energy are... All right, this is just conserved. Like, if you have like the chemical reaction, like let's say if A turns into B, right over here for like a chemical reaction, well, it has to have the same mass. The mass of A has to be equal to the mass of B. You cannot just generate mass out of nowhere. You are not an anime character. All right, let's be real here. All right, you cannot just create matter out of nowhere. It has to stay the same. All right, degree of polarity is by calculating the difference in their... All right, that's just going to be electronegativity. You should know this, but basically this is like a very important concept. But basically, the degree of polarity basically just tells you the difference in their electronegativity. So remember, electronegativity just basically it tells you how attracted is an atom to an electron. Okay, so the level of sort of attractiveness an atom has for an electron, and specifically when it's in a chemical bond. So let's take a look at H2O, water. Now, oxygen has a high electronegativity, meaning that it has a very high attraction for electrons, while hydrogen has a lower electronegativity than oxygen. Therefore, oxygen is actually going to sort of hog some of hydrogen's electrons. Right? The electrons are going to be closer to oxygen because oxygen attracts these electrons more than hydrogen. So yeah, that's pretty much it. All right, and the higher the difference in their electronegativities, well, the more that thing is going to hog, quote unquote, the electron. Which substance cannot be broken down by a chemical change? A substance that cannot be broken down by a chemical change is an element. Elements cannot be broken down by a chemical change. So that's going to be magnesium. All right, if we look at the periodic table, magnesium is right over here. It's an element. Elements cannot be broken down, right? If I have H2O, water, I can break this down into hydrogen and oxygen, but, elements can't be broken down. All right, describes the components of a mixture. All right. Well, the proportion of the components can vary. If I'm making lemonade, I love this example, but I use this example like every time. I swear, I love it. Let's say if I have lemonade right over here. Now, my lemonade can be, let's say, 10% water, and 90% lemon. Oh, that's a sour lemonade, right? Now, lemonade is a mixture because we are physically just mixing these two things together, right? They're not chemically combined. Now, lemonade doesn't always have to be that way, obviously, right? This is a very sour version of lemonade, but I can also have a lemonade where it's, let's say, 50% water and 50% lemon, right? So notice how the proportion of your components can vary in a mixture. It's not always like, 10% water, 90% lemon, right? It can vary. So that's why C is the answer. Table sugar can be separated from a mixture of table sugar and sand at STP by what? Water stirring by adding stirring and filtering. Okay. All right, I think this one should be number 4, and the reason why is because let's say if we have sand, let's say if the green things are sand, and let's say if white thing or blue things are my sugar. Now, let's say if I add water into this. So let's say if I had water into this. My first step is I add water. Notice how as I add water, my sugar is going to dissolve in the water, right? Sugar dissolves in my water. So then what I'm left with is just the sand, and I can just filter the sand out, and I get my thing. Distillation is used when two things have different boiling points. So then I just take advantage of the fact that they have different boiling points because I set the temperature of the distillation thing to, or whatever you're heating the mixture up with. I'll just set that to a certain temperature. One of the thing is going to evaporate, while the other thing is going to stay there, and then they get separated. All right. Kinetic molecular theory. particles of the ideal gas. All right. So the kinetic molecular theory basically, remember that it's a theory. All right. There's a difference between a law and a theory. A law describes what happens. What happens. While a theory describes why that happens. All right. So the kinetic molecular theory basically describe kind of how, or how particles move. So how do kind of gas particles move kind of ideally? All right. So theory, it's the why, it's the how, right? While laws, it's sort of like what happens. So for an ideal gas, what you have to realize is that the kinetic molecular theory, it's not number two. In fact, the kinetic molecular theory actually says that gas particles actually don't have any attraction between each other. It also says that it's also not number three. The kinetic molecular theory actually says that the gas particles move in random constant motion, right? Gas particles, they move randomly, constantly in whatever container they're in, whatever, right? So they're constantly moving in random directions, small distances relative to their size. No, it's not on number four. The particles, in fact, number one is correct. The volume of the gas particles is considered negligible. Basically, the volume of the gas particles is so small compared to the container that we can basically just say that the volume of this gas particle is basically zero, right? It's so small that it doesn't even matter. Because if we're comparing it to the volume of the container, this is going to be way bigger than zero, let's just say. It's way bigger than zero, all right? During which two processes does a substance release energy? All right. Let's think about this like this. Let's say we have an ice cube, we have some liquid water, and then we have gas water, the gassy. All right. Now, let's say if we were going from an ice to liquid water, what are we doing? Well, the ice, in order for ice to melt, it has to absorb heat. All right. So, yeah, in order for ice to melt, it has to absorb heat, so it can't be 2 or 4. Let's see evaporation. In order for water to turn into gas, it has to evaporate, right? So it has to absorb heat, right? Wait, what the hell did I just say? And in order for water to evaporate, it has to absorb heat, right? So it can't be C because evaporation absorbs energy. So it has to be 1, freezing and condensation, right? Notice how as I go to the right, this right over here represents processes that absorb energy. And you can imagine that processes that are going to the left, they actually release energy. When you're going from liquid water to ice, well, in order for water to get cold enough to become ice, it has to release all of that energy, right? So that it has less energy, so that it is ice. And same goes for condensation, right? When a gas turns back into liquid water. Based on table I, which compound dissolves in water and an exothermic process? Exothermic just means that it releases heat. Okay, guys, so I have table I right over here. Which compound dissolves in water by an exothermic process? So let's check NaCl. Where is NaCl? When this thing dissolves in water, there's a positive sign right over here. This positive sign represents your change in enthalpy. All right, change in enthalpy, or your heat of reaction. This essentially tells you how much heat is absorbed or released. Now, if your change in enthalpy is a positive value, that means it absorbed energy. And if you're absorbing energy, that's an endothermic process, not an exothermic process, so it can't be 1. So basically, if your thing is positive, that's not exothermic. All right, so NaOH. NaOH, that's negative, all right. So that, all right, NH4Cl. Let's just check the other answer choices for the fun of it. This is positive, so no. NH4NO3, this is positive, so no. So yeah, NaOH is the answer. I actually did an experiment with NaOH, and it was pretty fun. We had these like cups, and we saw how much NaOH kind of increased the temperature of water in a cup, because when NaOH dissolves, it increases the temperature. I can actually feel the cup getting hotter. It's actually pretty nice. At STP, which property of a molecular substance is determined by the arrangement of its molecules? Which property? Arrangement of its molecules. Well, half-life, molar mass, physical state, percent composition. I mean, it just has to be number 3. I mean, you can just think about this. You can just think about water, like the example we saw before. Like, because all the water particles in ice, they're very compact and they have something known as intermolecular forces, which are basically forces of attraction that hold all of these water molecules together. And because these forces of attraction are very strong, the solids are very rigid. And when these forces of attraction start to weaken, well, then that's when it changes its physical state, right? That's why we call it phase changes, right? So um, when it becomes a little bit weaker, then it becomes a liquid, right? And then the physical state changes. And when the intermolecular forces, these forces of attraction, they get so weak, it can actually become gas, or it kind of escapes, right? It's all separated from one another. So yeah, that determines, how the molecules are arranged. Equilibrium can be reached by both physical changes and chemical. Yeah, it can be done by both physical changes and both chemical changes. The kind of thing I like to remember is that, let's say if we have water, let's say if this is liquid water, it can be at equilibrium with water that's in a gas phase, right? Let's say if we have water in a sealed container, so let's say this container is sealed. This is the lid, right? And let's say if this is the water right over here. Now some of the water is going to evaporate, but because the container is sealed, none of the water molecules are escaping, and some of that water that just evaporated is going to condense and go back into a liquid. So basically, the rate of evaporation is the same as the rate of condensation, and that's when this is in equilibrium. And you probably know some reactions in equilibrium. I like to know the Haber process. And actually, let me see if I can actually find a reaction on the thing. Never mind. I did not find. I thought there would be like some reaction here where it's like a double arrow, but it doesn't show. So yeah, the example I like to do is this plus N2 is at equilibrium with NH3 to NH3. This is the Haber process. I like this one. Which value is defined as the difference between the potential energy of the products and the potential energy of the reaction during a chemical change? Potential. That's just going to be the heat of your reaction. The heat of your reaction, that's the same thing as the change in enthalpy. All right? When reactions happen, right, the potential energy of the products, the energy of the products is going to be different. Sometimes it's going to be different than the energy of the reactants. And that's going to be your heat of reaction, right? It's just going to be that change in potential energy, right? Sometimes it releases heat, sometimes it doesn't, and it's endothermic, right? It absorbs. All right. I want to answer these ones, but I'm a little too lazy. So yeah, that is all. Please pay for my rent, guys.